Hi, I'm Nick Frosst, and I'm going to be talking today about certifiable robustness to adversarial attacks and why and if we would even want that in the first place. A quick preamble. This talk will mainly be opinion, and I'm very open to it being wrong. So if during this conversation I say some things that you totally disagree with, feel free to jump up and say I object very loudly and dramatically, or to talk to me about it afterwards. First of all, how many people know what adversarial attacks are? How many of you have seen this exact slide before? Yeah, it's the same group. Okay. For the small number of you who didn't know, who have not been bombarded with adversarial attack literature and discourse yet, quick overview. An adversarial attack is an input that has been intentionally crafted to fool a machine learning system. So specifically, what we do is we take in this case, an image classification system. It has been trained to classify images, and an adversarial attack is an input to this network that has been changed maliciously so that it is indistinguishable to a person, but that a neural net system gets incorrect. So in this case, it's a panda, but when we add this noise pattern multiplied by a very small number, you don't see the difference. This panda looks like this panda, but the network classifies it as a given. So when this phenomenon was first discovered, many researchers were very worried about it, and they began working on how to defend against these attacks. So this takes many different forms. One of them is just making neural nets that perform better on such attacks. One of them is trying to figure out what is an attack and what is normal input. But all of the work around adversarial attacks falls into this same cycle. And the cycle is somebody presents a defense or a detection mechanism and says, look, we are robust to adversarial attacks, meaning we either can classify them as adversarial or we classify them correctly, and they publish a paper about it and they get a bunch of citations, and then a couple months later, someone comes along and makes a new adversarial attack that breaks this defense or breaks the detection mechanism. And that has been going on for many years now, with many different cycles. And this has been frustrating for a lot of people because they saw this phenomenon of adversarial attacks and they really wanted to solve the problem, thinking that it was a big deal for neural networks. They proposed some new method only to have it be broken later. So this is a pervasive thing, and it has not been solved yet over the several years that it has been studied. This led a number of other researchers to try to get ahead of the cycle by creating provable robustness to adversarial attacks. So before the papers that were written about adversarial attacks robustness, they would do their own experiments, and they would say, look, we tested against these known attack strategies. And by attack strategy here, I mean a way of finding this noise. So there are many different ways for finding that noise, the simplest of which is just follow the gradient of the model with respects to increasing the loss. But there are other ways of doing it, so that's an attack strategy. So people would create a defense. Then they would test out their model on as many attack strategies as they could find, and they would show robustness on those attack strategies. Someone would later come up with a new attack strategy and it would break the model. But they wanted to get ahead of this by saying, can we prove that our model will behave the same under any epsilon perturbation? How many of you are familiar with the idea of epsilon perturbations and like bounding? Okay. So smaller than the number of people who are familiar with adversarial attacks. That's interesting. So an epsilon bound, epsilon here just means a really small number. And an epsilon bound just means that we're going to prove that our network is going to classify everything correctly, given that it's within epsilon of some correctly classified input. So if we could do that, and we could say, given that we classified some test case correctly, we prove that everything within epsilon of that image is also going to be classified correctly, then theoretically, we shouldn't have to worry about new attack strategies because we've already proven that any epsilon change to the image will result in the same classification. So that looks something like this. So here we have this same image, this same epsilon, same noise pattern multiplied by epsilon, this small number, and the adversarial example. And here we have visualized a high-dimensional decision boundary based on the input space. So this is a two-dimensional representation of it, but imagine it's actually much, much higher dimension, and just say 2 dimensions in your head over and over again. Here we have like an epsilon bound. So here's one decision boundary, here's another decision boundary, here's a third. if we can say that everything within this green ball is going to be classified correctly, or sorry, classified the same as everything within, as the center point, then we can say that that is provably, certifiably epsilon robust. And as long as that decision boundary doesn't cross over these, doesn't like cross into spaces that look like something else, this should be fine. So here, in this example, if this adversarial input here is outside of that epsilon ball, then we can't make any claim about it, and this could be classified as whatever we want. So in this setting, the epsilon bound is obviously not big enough, because this looks like a panda, and this looks like a panda, and these are not within, we haven't proven certifiability within that range. So we'd want to expand this, and then we'd want to prove that we're going to classify everything correctly there. So the general research program here has been to figure out ways of growing that epsilon certifiability and proving that everything is going to be classified homogeneously within it. One way that people have done this is with something called a Lipschitz constraint. Another poll, how many of you have heard of Lipschitz constraints? Okay, cool. So a Lipschitz constraint effectively just means it's a property of a network, sorry, not of a network, of a function, and it just means that as the input to that function changes, the output of that function is going to change in some bounded way. So this little GIF over here kind of visualizes this. And you can see that there's this cone. If this function satisfies a Lipschitz constraint with this cone, it means that the output of this function is never going to fall within this cone. So if this slope was like much faster, if it grew a lot higher, then as the cone shifted, part of it would fall within it, right? But here, because the change in y doesn't change that fast with respect to the change in x, nothing ever falls within that cone. Does that make sense? Okay, so that's a two-dimensional representation, but you can imagine that same property in a much higher dimension, where the input, the x, is an image, and the output is the classification. And we're going to say that as long as if the image changes a little bit, then the output, the classification, is also only going to change a little bit. And so that's one way that we can get towards certifiable robustness. If we prove the Lipschitz constraint in a network, then we know that you're going to have to change the input a lot in order to change the output a lot. Does that make sense? Yeah. So lots of people have written about this. Actually, that number is not very visible, but it's big. There's a lot of papers written on certifiable robustness, and a lot because it's a promising direction. It's taking this cycle that has been ongoing and trying to get ahead of it by getting something that can prove it won't be broken in the first place. But I'm not sure why. That's mainly what this talk is going to be about. Yeah. So why exactly did people do this? What was the motivation? What is the benefit? All of these things are up for debate. First of all, when you talk about epsilon robustness, really what we're saying is that a small change in the input is going to have a small change in the output. But what exactly is small in the context of images? In the literature, small means like distance-wise small. Like we treat the image as a big vector, and we measure the distance between that vector and another vector. And we can use cosine similarity, or we can use L2 distance, or L infinity distance, whatever, any number of distances. But it's still an arithmetic distance. And we make the assumption that a small change in the image, a small change in this distance metric, is going to result in visual imperceptibility. That's what set off the whole fever of adversarial examples in the first place, was that we looked at the gibbon, at the panda, and the thing that's classified as a gibbon, and not only does it look like a panda to us, but it's indistinguishable. The change is so small that we can't tell the difference at all. But we know that distance metrics, Euclidean distance, is a bad approximation for visual similarity. So this was in a paper that came out a while ago that addressed adversarial examples in general, and it pointed out that all of these things, all of these faces, are equivalently far away from this reference image. So if you measure the distance between any one of these, it will be the same number. And yet these look completely different, and many of these are obviously visually dissimilar to this one. In essence, the reason for this is that your eyes are measuring the relative properties of an image. So this one to this one, can you guys tell that this image is a lot brighter than this one? Yeah. But if I just showed you them kind of quickly, you might think that they look the same. That might be the case for that given one, for the panda earlier on. I don't know. The point is that when you look at an image, you look at the relative change in things, and you try to put some semantic meaning on it. You're not looking at the raw pixel values. And so these two things that have very different raw pixel values look pretty much identical. Well, you can kind of flip that on its head and have two things. Here now we've kind of inverted it, so it looks like the face is almost like indent because all of the lighting has been changed. But these have the same distance and yet are still really dissimilar. So there's an assumption saying if we could prove certifiability then, to some epsilon perturbation, then we know that the network would classify all the things within that bound the same, and that would be good. And the reason why that would be good is that all the things within epsilon are going to look identical. But that isn't true. We know that small changes can result in very large visual perception changes, and so maybe the network ought to handle them differently. So some of our recent work in the Google Brain Group in Toronto has been on creating models that find these examples that are very close together in terms of Euclidean distance, but are not only visually dissimilar, but are semantically different. So this 0 and this 8 are within some normal, like some very small epsilon bound of each other. I think it's like 16 over 255, which is the pixel value. And yet, one is obviously a 0 and one is obviously an 8. That is also true for this 1 and the 2, 2 and the 1, 3 and the anyways, the whole thing. These are SVHN digits, by the way, so these are natural images that you can find examples that are within epsilon of the test set, but yet are not only visually dissimilar, but of a different class. So if we had a model that was certifiably robust to an epsilon perturbation, that is to say that the output of the network didn't change very much when the input to the network didn't change very much, it would necessarily get all of these ones wrong. It would if it got these ones correct, it would get these ones wrong. Conversely, if it got these ones correct, it would get these ones wrong. So this means that a certifiable network will make mistakes that we obviously don't want our network to do. Now, we tried to do the same thing on CFAR, and it worked sort of, but a little less. Here we can kind of see that to go from a dog to a deer, it extended to the ears and made some of the features slightly more deer-like. Or to go from an airplane to a ship, it kind of turned the tarmac into water. But these are at least ambiguous, and obviously the changes may be semantically meaningful. One of the reasons why our strategy hasn't worked so well on the CFAR stuff is related to the reason why epsilon is not a good measure for epsilon certifiability is not something you necessarily want to have a network to have, is that our strategy is relying on the distance between two images to measure how visually similar they look, and we know that in natural images, the distance is not a good metric. Is that 2 minutes?
So are these images distinguishable by, never mind the issue at hand, are these images, paired images, distinguishable by image recognition?
By like current settings? I mean, they're recognizable on the, yes, the answer is yes. There's like a particular network and architecture that we're working with that is able to tell the difference between these two.
But they are particularly tricky for typical.
Yeah, presumably they would be difficult for regular standard neural nets. I haven't done this other little bit of research that I would like to, which is take these images and then apply them to normal neural nets and see how they behave. Because they should represent kind of hard examples in that in a numeric sense, they're very close together, but in semantics, they're very far apart. So it should represent an interesting case. There's a further future research that we hope to do in that direction. So the first problem is, do we even want things to classify things the same within an epsilon bound of some image? Well, maybe not, because they might look very dissimilar. Secondly, it turns out that not only can they look dissimilar, they can be semantically different. So we know not only is it maybe not a good idea, it also will necessarily get things wrong. And finally, we're not even sure if we should care about adversarial examples in the first place. So this is a slide I and many other people have used before, which is just to say that when someone talks about adversarial examples, their go-to is to say, oh no, a driverless car might be fooled by an adversarial stop sign, in that you could go up and make a small perturbation to the stop sign and it might interpret it as a speed limit or not a stop sign or something, and that would be an issue. But lots of people posit that if you wanted to mess up an autonomous vehicle, you could just knock down the stop sign. And there are many situations where it turns out that taking the gradient of some network that you have access to and making a small epsilon perturbation and then giving that epsilon perturbation back to the image and then getting it to classify isn't really the best way of screwing up a network. You can normally just break the computer. And like that, there are many situations where, I mean, moreover, I am someone who has been looking at adversarial examples for a while and I'm still not aware of any real-world application of them. So that's a point I'm willing to be wrong on. If anybody really has like an example, I would love it if they came and told me, but I don't know of one yet. And maybe that's bad? I don't know. Maybe it's not. That's the other question. Maybe it's not so important that like the destination or that the objective was good. Maybe it's the friends we made along the way and the things we learned that were the true treasure, you know? And that's to say, maybe, so like one of the examples, so the Ellipses constraint stuff, where you try to say we have a network, and if we make a small change to the input, we want a small change in the output. That has been used in many other areas in machine learning. So notably, there was a poster outside from some people from the Vector Institute that is about the invertibility of invertible networks, and they found that if they have a Ellipses constraint on these networks, then they're more invertible. So I was going to tell you, like, this is great. It probably means that they got motivated by the literature from adversarial examples and the Ellipses constraints that were used in certifiable robustness, and they're able to make use of that work to get some other cool desirable property like the invertibility of invertible networks. So before this, I went and I asked them and I said, hey, did you look at the adversarial literature on certifiable epsilon robustness? Did that inspire or motivate you? And they said no. So that's too bad. They said no, but then they also said, but maybe, and that maybe they only heard about Ellipses constraints because other people were working about it. I don't know. The first time I heard about Ellipses constraints was in the context of adversarial robustness. It's also used for things like generative models, where you can make sure that as the input, that you have kind of a smooth transition between your latent space and the output of a network. Maybe that's a good property. I don't know. Maybe this is the way science progresses normally. Like maybe it turns out that lots of people do research on things without really thinking about the utility of them, without really stopping to formulate the problem or establish what their goal is, and maybe that's great. Maybe we got chemistry from alchemy, and maybe that's the way science ought to be. I don't know. I think it's more likely that the adversarial stuff and the fever around it and the attempts to create certifiability to a problem I don't think exists came from really great headlines in news articles. I think it has something to do with the fact that like it's a very easy narrative to say we are attempting to solve a security issue in neural networks. And I think that's a very evocative thing to work on. So I understand why lots of people did, and I understand why there's thousands and thousands of papers on the topic at this point. But I don't know. And I'm very curious as to the history of this particular like vein of machine learning, and I'm going to be really interested to see if A, I'm wrong and it turns out that adversarial attacks were super important and the only way to defend them is Lipschitz certifiable constrained networks, which could happen, or it could be the case that in a couple years the invertibility thing becomes really great and it's super important and we really needed Lipschitz constraint, and when I go ask the researchers who have been working on that, they say, wow, if it wasn't for certifiable networks, I never would have come to this conclusion. So we'll see. That's an open problem. I think that's kind of all I had. That's the end of my slides. And I have 1 minute left. So if anybody has any questions, I would love to take them.
Hi. It wasn't a question per se, but my understanding would be for adversarial attack, it would be really useful for face recognition on the cameras we have. Like, let's say, I would say not useful for security, but would be for someone if they don't want to be recognized on their cameras or something, they can have adversarial attack on that sort of camera that they do, like face detection, for them to realize, like, let's say who the not the person who shouldn't be there is there. So
Yeah.
that is like, I feel like that would be the most applicable application of the adversarial attack.
Yeah, for sure. So I think it's important, like, given that we're deploying machine learning systems and we're not always going to want them to be deployed, it's certainly important to think about how you could subvert them. And there are like many real-world applications going. I mean, you can look at stuff that's going on in Hong Kong right now as being an important application of figuring out how to get around facial recognition software. It just turns out that making a small epsilon change to your face is not the best way to do that. If you want to wear a mask, you can wear a mask is, I mean, as the Hong Kong protesters have adopted, masks are better ways than like making small pixel changes with makeup or something. I mean, furthermore, if you want to wear somebody else's face, like there is a whole field of prosthetics and makeup art to make you look different.
But I mean, if you wear a mask when you're in an airport or somewhere that you don't want to be seen, then you are being seen by wearing that mask. But you won't be detected under the cameras.
Yeah. But I just think the better solution for that problem would be to just apply makeup in the way that like spies and
so
play authors have been doing to look like a different person, as opposed to measuring the distance between an image of your face and the image of your face slightly changed. Yeah. But yeah, no, like, it is important. I don't disagree with the idea.
But again, facial would be applied to like more like a structure. Like how much makeup you're going to put to change the structure of the face. I mean.
Yeah, actually, sorry, wait, I guess to put it succinctly, the assumption in the certifiable robustness literature is that if you make a larger than epsilon change, people will notice. And so we only care about epsilon changes. But that is not true in the setting you're describing. If you had really good makeup on and you looked completely different, but you didn't look like yourself, but it was convincing, I wouldn't, like, that's still an issue. I wouldn't notice. It would fool the classifier. So the epsilon constraint isn't imposed by anybody but the research community.
I see.
Yeah.
Thank you.
No problem.
Yeah, so actually that already exists. It's called Face Shield, developed by somebody called Joey Bose. He's at Mila now. But the question I had for you was, like, if we just assumed right now that adversarial attacks are actually a problem, and
wait, what? Did you listen to my talk? What?
Okay, but be a sport, right?
Okay.
And we were saying that this whole like robustness approach, this epsilon ball, is the way to do it. Are we not just? I mean, I'm on your side here by this question, and I'm saying, like, are we not just sticking our head in the sand by saying, like, okay, so I have this photo, and now this photo is adversarially robust, and now this photo, and my entire data set is adversarially robust. But if the panda just had a bad day and it was raining and he went to his hairdresser wasn't there and he got a bad haircut, and then like they took his photo with a Game Boy Color camera, and somebody did an adversarial attack on that image, like the point I'm trying to make is that you only end up inoculating yourself for the data set that you've trained on, and you're not inoculating against generalized attacks on other images that you're supposedly able to generalize on.
Yeah. Okay. So I think I understand your point, and I think when you're talking about the Game Boy, you're alluding to I think the real issue here, which is distributional shift.
Exactly.
And the main problem is that we trained on a training set, and then we measure the performance on the test set. And then we as people look at the similarity between those two distributions and extrapolate to a much broader set of distributional shifts. And that's the real problem. And adversarial examples are one distributional shift. Like adversarial examples, they're not in the test set, so our networks don't perform well on them, and then we're surprised, and the reason we're surprised is that they look the same to us, so we extrapolated from the performance that it should get these things correct.
Yeah.
Now, in your example of like the Game Boy camera, I think you mean like if normally you take photos with one camera and then suddenly you take another, and we perform an adversarial attack on there, who knows how the network's going to behave? But even worse than that, our networks, like the image classification systems we have, aren't robust to things like XY translation or like scale, or like let alone a different type of camera being used or a different pixel value.
That's basically my point, is that if you already have a distributional shift, your model is going to maybe have some trouble, and then you do an adversarial attack on that. I just don't see the point in doing robustness in the first place on your original distribution, because it's naive to think that something that you're building for generalization is inoculated against attacks on the one thing that doesn't need to be generalized on.
Yeah, I agree. I just think even a step beyond that is that we ought to just worry about generalizing as opposed to the adversarial robustness.
Yeah.
Yeah.
Sorry. Hi, thanks. So I guess what this talk reminded me of, and I was thinking, was the trend in mathematics to do questions for question's sake as opposed to for application's sake.
Yeah.
Where I'm trying to just solve something, not worrying about like what the end goal is. And often that's a difficult thing to do because there's no backing or financial impetus.
Yeah.
But sometimes we often find that coming 50 years, 100 years down the road, that ends up being useful. I think that's what you alluded to with the whole idea of the Ellipses constraint. Do we feel that maybe what's happening is some of the research we're doing in ML and data science and such is, obviously we're starting off with applications, we're trying to solve problems, to get buy-in, to get people to, fund this research. But are we getting to a point where there's enough sort of interest and buy-in that we're switching to that more pure sciencey, pure mathematical model where maybe there's space and maybe it doesn't matter that there isn't a good why.
Yeah.
That maybe there's just space for people to answer questions for the sake of the question and figure out why that's good later.
Yeah, so I hope that's what we're getting to. And I gave a talk on why I don't think adversarial examples are important, and I have been working on adversarial examples for 2 years now. So, and I do it because I think it's interesting, and I do it because I think there's some nice properties, and I think it's a fun thing to work on. And so I hope that we are getting to a point in machine learning where it's well established that machine learning is a good idea, and that we can try to make it better without alluding to security threats or dangers that need to be solved. I hope that's what we're getting to. That's the reason why I do adversarial examples literature, and that's why I work on trying to get networks whose gradients happen to look like real images, not because it solves any problem, but I don't know, I think it's pretty, and that's important. But that's also a very privileged place to come from as a researcher who's employed in a large company that allows people to do research for research's sake. That isn't the situation that many researchers are in, where they're in universities competing for grants, needing to get things that they think are relevant. So there's a much broader conversation to have about the nature of scientific research and its current implementation in today, and how we can get more people just doing things for research's sake. But I'm not going to solve that in the next 2 minutes. Yeah.
Last question.
Great talk. I was just curious whether, as you're going through this process of almost uncovering the very essence of maybe a collective delusion, perhaps, would you think that there are other areas where we worry about things simply because we're just afraid of change? Do you think that this is somewhat related to machine learning being applied, in people's lives, and people, because it's new, thinking, where are the holes? Have we figured it all out? How is it being exploited? And then that kind of maybe feeds into trying to go after these things.
Tough question. And I think it's tough because, yes, I do think that. I think there are many examples where I think there are many examples of the story I just told applied to other things. But conversely, I think there are many stories that are being missed entirely. And there's lots of conversations going around on the application and deployment of machine learning systems that are super important and that have ways of changing our lives in drastic ways, in a non-Lipschitz constrained way, in a way where a small change to the deployment will have a huge effect on the output and the result of the deployment. And those conversations are not being had. So yes and no, which is barely an answer, but tough question. Yeah, cool.
Thank you so much.
Great, thanks a lot.